video, and today we are going to discuss about the Raoults law. But before discussing the Raoults law, let us first learn the very important topic that is called vapor pressure. So what is the vapor pressure? See, let us have, this is a container in which some liquid are placed and it is enclosed by a bell jar. You know well that this liquid has the inherent property to escape from leaving the liquid state and forming the vapor. It is because of the very high kinetic energy of the liquid molecules of the uppermost layer. So what will happen? Because of the high kinetic energy, this liquid molecule will start slowly evaporating and forming the vapor. And as this vapor is enclosed with the bell jar, this will not escape into the surrounding. So what will happen? After some time, an equilibrium will exist between the liquid and the vapor. That means at this instant, the rate of evaporation of liquid and the rate of condensation of vapor becomes same, and at this stage the pressure exerted by this vapor over the surface of the liquid is called vapor pressure of that liquid. So how the vapor pressure can be defined? The vapor pressure may be defined as the vapor pressure of a liquid or a solution is the pressure exerted by the vapor on the surface of the liquid or a solution in equilibrium at constant temperature. Understood? Once again I am repeating, the vapor pressure of a liquid or a solution is the pressure exerted by the vapor on the surface of a liquid or a solution in equilibrium at constant temperature. Now, we will have to know the factors on which the vapor pressure depends. There are very important 4 factors. First one is the nature of the liquid. If the intermolecular force of attraction between the liquid molecules is very weak, the liquid can easily form the vapor, so it will have very high vapor pressure. Second factor is the temperature. With the rise in temperature, what happened? The kinetic energy of the liquid molecule as well as the random motion of the vapor molecules go on increasing, so the vapor pressure will go on increasing. So with the rise in temperature, vapor pressure of any liquid go on increasing, which can be mathematically expressed by Clausius-Clapeyron equation. Clausius-Clapeyron equation is log P2 by P1 equals to delta enthalpy of vaporization divided by 2.303 into R multiplied by T2 minus T1 upon T1 into T2. What are these terms? Where T1 and T2 are the temperature at which the pressures are P1 and P2. Vapor pressures are P1 and P2, and delta HV is the enthalpy of vaporization of the liquid. And the third factor which affects the vapor pressure is boiling point of the liquid. A liquid having less boiling point means the liquid is more volatile. That also means that it has more tendency to form the vapor. So obviously, liquid with lower boiling point will have greater vapor pressure. And the last factor which affects the vapor pressure of a liquid is the purity of the liquid. So what happened? In a pure liquid, the uppermost layer are occupied by the liquid molecules only. There is no other molecule. So every surface, from every point, the vapor will get formed. So it will have high vapor pressure. The moment some substance is added, so on the top of the surface, what will happen? Some surface will be occupied by the added substance, while the other are occupied by these liquid molecules. So obviously, as the number of liquid molecules on addition of a substance get decreased on the surface, so its vapor pressure decreases. That is why it is said a pure liquid has always higher vapor pressure than its solution. So this is all about the vapor pressure. Vapor pressure is the pressure exerted by the vapor on the surface of a liquid or a solution which is in equilibrium with its vapor at a given temperature. The factor which is affecting the vapor pressure are nature of the liquid, temperature, boiling point of the liquid, and the purity of the liquid. Now, we will discuss about the Raoults law. What does the Raoults law express? Raoults law says that in a solution, the vapor pressure of any component is directly proportional to its mole fraction. More will be the mole fraction of the component, more will be its vapor pressure. That means let that a substance, a particular component A in any solution has partial vapor pressure PA. So PA will be proportional to its mole fraction XA, and after you know well that this proportionality sign has to be replaced by a constant. So PA will be PA naught into XA. PA naught is the vapor pressure of the pure liquid A. So partial pressure of any component is the mole fraction multiplied by its vapor pressure in pure state. This is the basic definition of Raoults law. Now we will consider the two cases. The first case is the vapor pressure of a liquid solution. That means both the liquids are volatile in nature and are forming a liquid solution. This is, see here, we have two liquids A and B, where A is solute and liquid B is solvent. As you know that this is only containing, this vessel is containing only liquid A, it has no other substance, so its vapor pressure is said to be the vapor pressure of the pure solute, that is P naught A. This is the solvent only, so its vapor pressure, it is in the pure state, so its vapor pressure will be P naught B. Now, in another container, XA mole of A, which is solute, and XB mole of solvent are added. So what will be the vapor pressure? Vapor pressure of, you know here that in this solution, what is vapor pressure of solute is greater than the vapor pressure of the solvent. That means what? The intermolecular force of attraction between the solute particles is less as compared to the intermolecular force of attraction between the solvent particles. So obviously the vapor pressure is differing. So why it is? Because here PA will be proportional to the XA. So PA, partial pressure of the component, that is which is solute, is equals to its mole fraction multiplied by the vapor pressure in the pure state, that is PA equals to P naught A into XA. Similarly, the vapor pressure of the component B, which is solvent, will be partial vapor pressure of the component which is solvent B is proportional to the mole fraction of B. So PB is proportional to XB, and therefore PB equals to P naught B into XB. As both the vapor are enclosed in the same container, so what will be the total vapor pressure? The total vapor pressure, it will be equals to PA plus PB, isn't it? Total vapor pressure is the vapor pressure of the component A, which is represented by these hollow spheres, and the vapor pressure of the solvent component B, which is represented by lines in the oval. So what you see, there are 4 empty ovals, which is the solute whose vapor pressure is more, and only 3 circles containing lines. Why? Its vapor pressure is less. So total vapor pressure will be the sum of the partial pressure of both the component PA plus PB. Here PA is the P naught A into XA. Substitute this value. PB equals to P naught B into XB. So P total will be P naught A into XB plus P naught A into XA plus P naught B into XB. But as you know well that in any solution, the sum of the mole fraction of all the components cannot exceed 1. That means if the solution is binary, having only two components, one is solute, other is solvent, the XA and XB will be equals to 1. So XB will be equals to 1 minus XA. Now in equation, let it be equation 1, it is equation 2 in equation 3. So in equation 3, we will replace XB with 1 minus XA. So P total will be P naught A into XA plus P naught B into 1 minus XA. Now solve this. It will be P naught A into XA, and this part has to be multiplied by P naught B. So P naught B into 1, P naught B, and plus minus minus P naught A into XA. So keeping this P naught B, it is a constant, pure vapor pressure of the pure liquid B, and this is here P naught A into XA has plus sign, here P naught B into XA has minus sign. So keep the plus sign in before the minus sign and take the XA common. What will be? It will be P naught B plus P naught A minus P naught B into XA. This is the P total. This is what is the total vapor pressure according to Raoults law of a liquid solution containing two volatile liquids, which is a binary solution. Graphical representation of this Raoults law for the liquid-liquid solution. See, what is the equation 3 here? You know well that expression for a line passing through origin equals to y equals to mx. Here also y equals to mx. But here for equation 3, y equals to mx plus c. So now put the value here. When xa equals to 0, this entire term will be 0. So P naught V will be 0. Here. This is the axis representing the vapor pressure of liquid B and A respectively. This is representing B, this is representing A. So here when you will keep the value of XA equals to 0, XA equals to 0, so in this entire term will be 0. That means it will be P total will be P naught B, and P naught B, that is the vapor pressure of the pure liquid. So this is XB equals to 1 and this is P naught B. It is the vapor pressure. Here what we have taken, P naught B is less than P naught A. That means this more P naught B is vapor pressure of the liquid B is less than P naught A. P naught B is the solvent and P naught A is the solute. So here what we will take, XA equals to 1. So when you will take XA equals to 1, what will happen? See here, XA equals to 1. So it will be P naught A minus P naught B. P naught B cancel out. So XA equals to V. The total pressure will be equals to P naught A, sorry. At P naught B cancel out. It will be total pressure will be equals to P naught A, which has higher value. So it will go here. Now join this line, origin here, Here mole fraction of B equals to 0, mole fraction of A equals to 1. Here mole fraction of A equals to 0 and mole fraction of B equals to 1. So this line represents the partial pressure. This is PB. This is representing PA. And when you will add this point P naught A into P naught B, this is the P total. This is representing the mole fraction. So this is the graphical representation for Raoults law. If it is ideal in nature, that means they are perfectly miscible. The two liquids must be miscible. They are forming the homogeneous solution. Now, after this, we will discuss the case 3. Case 3 is the, see here, case 2. Case 2, when a non-volatile solute is added into a volatile solvent. So what will happen in this case? Non-volatile solute is added into the volatile solvent. So what will happen? It is solid particles added into a volatile liquid. So some solid particles will occupy the surface. That means on the surface, the particles of the liquid will be less, so its vapor pressure will be less, which is called partial pressure of that liquid. So partial pressure of that liquid will depend how many mole fraction, how much mole fraction of that liquid is present in the solution. So again here PA equals to P naught A into XA, where PA is the vapor pressure of the solution, P naught A is the vapor pressure of the pure liquid, and XA is the mole fraction of the solvent. From here we can derive the relative lowering in vapor pressure. So the vapor pressure of the pure liquid, that is A, is P naught A, and the vapor pressure of the solution is PA. So what will be the lowering of vapor pressure? Lowering of vapor pressure is the vapor pressure of the pure liquid, that is P naught A, minus vapor pressure of the solution PA. So P naught A minus PA. Now substitute the value of PA. What is PA? It is the product of the two terms, mole fraction of A into vapor pressure of pure liquid A. So replacing PA by P naught A into XA, we will have delta P, lowering of vapor pressure, equals to delta P naught A, take it as a common, 1 minus XA. That is 1 minus XB. Why it is? It is because XA plus XB will be always equals to 1. So what will be 1 minus XA? If 1 minus XA will be equals to XB. So that is what. So divide this, bring this P naught A below here. So it is lowering of vapor pressure by vapor pressure of the pure liquid A. This is called relative lowering of vapor pressure, and that is equals to the mole fraction of solute. XB is the solute present in the solution. So this is the relative lowering of vapor pressure, which is a colligative property. Relative lowering of vapor pressure depends on the mole fraction of solute XB. Now, what will be the mole fraction? Mole fraction, that is relative lowering of vapor pressure, mole fraction delta P by P naught A will be equals to mole fraction of B, means NB by NA plus NB. This is for very dilute solution. Dilute solution, what will happen? NB, moles of solute, will be much lesser than Na. So therefore P delta P by P naught A will be equals to NB by NA, mole fraction of added solute by mole fraction of this liquid, pure liquid. This will be how we calculate the mole? Mass by molar mass. So it will be equals to WB by MB into here WA by MA. That will be delta P by P naught A, or MB molecular mass of solute will be equals to how much? WB by delta P upon P naught A into WA here MA, relative lowering of vapor pressure. So using this we can calculate the molecular mass of solute, and often in the board examination there are numerical problems based on the relative lowering of vapor pressure. So what you will, revise this topic. It is very important for the board examination, and also attempt the in-text question assignment. What are the assignments? Solve the in-text questions, and exercise problems based on Raoults law from NCERT book. In my next video, we will discuss about the ideal and non-ideal solution, and after that we will thoroughly know about the azeotropic mixture and their types. Till then, goodbye to all of you, and do revise the relation properly. Thank you.